All right, so today we're going to be starting in on the trigonometry unit. Okay, so we're going to be playing with this for a little while. It's actually not too bad. It actually is just a heck of a lot of algebra, but you're going to be playing with lots and lots of nasty-looking decimals. Don't worry. I would say that 99% of all of the answers you're going to wind up getting are going to be evil-looking decimals. Don't worry about that. Are you okay, Juan? Yeah, that's what I thought. Thanks. All right, let's see if we can break up this word and understand what we're looking at. Metric, meter, what do you think about? Measurement. Try. 3, right, good. And we've seen the prefix, or in this case it's an infix, gon. Where have we seen gon before? G-O-N. Yeah, polygons. And what did we say that meant? I mean, when we think of a polygon, poly means many. So polygon, many sides. So this is saying three-sided, or three sides measurement. So we're measuring three-sided things. So what are we really measuring? We're measuring triangles. Okay. So the study of trigonometry is the study of triangles and the angles that are in them and the lengths of the sides and how they're all related to each other. Okay. So we are going to be playing around with right triangles only. Not going to be fooling around with obtuses or acutes, scalenes, or, well, not true. We're going to be playing around with right triangles only, okay? If you decide to take Algebra 2 Trig next year, you'll play around with non-right triangles. Or if you take any of the other math classes after that, you'll be playing around with non-right triangles where things get a little funny. But right now, it's all right triangles. All right. Another thing that we have to know before we fool around with this is making sure that our calculators are ready to use. Okay, because this is something that pops up often, especially when you have a class with the calculators being used by different classes. Everyone look at your calculator. Find the mode button at the top. Push it and make sure that you are in degree mode. If you are highlighted onto radian mode, switch it over to degree mode. All the stuff that you will be using with me is in degree mode. Now, I'm going to tell you another thing. This is a little bit sneaky. On the SOL, I have to reset your calculator, okay? And when I reset your calculator, it goes back to like factory settings, okay? And the factory setting is in radian mode, which means that when you sit down on with your calculator on the day of the SOL, you have to put it in degree mode. I can't. I am not allowed to put it in degree mode for you. And if you try and do any of the problems on the test in the wrong mode, if you're in radian mode, you'll get them all wrong. Okay? So it's really important that you do this and that you know to check it. And now I also teach a calculus class, and that class is right before yours. Okay? They use these calculators from time to time also, and they use it in radian mode. So not just on the SOL, but when you pick them up walking in this room, you should pick them up and check. Because if you do them, like I said, if you just start crunching away and you're in radian mode, boom, done, game over. You're out of luck. You're going to waste all your time doing wrong problems, okay? So please learn to check for degree mode, okay? All right. Okay, so for example, let's press the following buttons for me. Okay. Okay, check this out. Hit second, quit. Now hit second, and then plus, I believe. No, yeah, second plus, which is mem, right? And then hit 7, and then hit 2, and then 2. Okay. Okay. Now clear and go to mode. Are you in degree mode or radian mode?
Oh no, you're right. Radian.
Yeah, it says that it's in radian mode. So push down until you're in the choices, and then push right to be in degree mode and hit enter. And then you'll stay on degree mode. Okay? You cool? All right. That's important. And by the way, that, second plus 7, 2, that little sequence of numbers that you just pushed to reset your calculator, if your calculator gets all funky and you don't know what the heck just happened, and like you're in some menu and you don't know how to get out, something's really weird and your graph is like not working the way it's supposed to work, just do that. Second memory, reset. Start over. Clear the screen, resets everything normal, brings it all back the way it's supposed to be. It's a nice little trick to get yourself back to home base, okay? If you need to. Anyway. So, trigonometry. Let's talk about a right triangle. We already know some relationships. We know some properties. We know Pythagorean Theorem. We know biggest angles across from biggest side. You can tell me who's a hypotenuse and who's a leg, right? All that stuff. You know all these things, don't you? Lie to your teacher. Okay. So, this is my hypotenuse. Okay. So, in right triangle trig problems, the stuff you're going to be working on, we are going to be talking about the relationships between angles and sides. Okay? If an angle gets bigger, then the side across from it is going to get bigger as well. You see? Like if I take this guy for a minute, and for example, if I change the length of this, if I change that angle, see this angle up top and this length down below, they change. When one gets bigger, the other one gets bigger. When one gets smaller, the other one gets smaller, right? Okay, now this little symbol that I just drew up here has got a name, and you're going to see that name a lot. You're going to see that symbol a lot, so I'm going to introduce you to it. Everyone, meet theta. It is pronounced, it's spelled T-H-E-T-A, but it is pronounced theta, okay? It's not theta or anything like that, okay? And what does it mean? It's saying, hey, look at this angle. It's a variable that represents an angle. It says the number of degrees that that angle is. So theta is just saying, like, in a sense, it's like x, but it's always talking about an angle, okay? And the thing that's important about it is that it's the angle that we care about, okay? If you're thinking about this for a minute, if you're standing at theta, if you're standing at that vertex, imagine yourself in your mind's eye, if you were standing where that guy is standing, you would be out looking, and let's give some guys this name. You don't have to write this down. I'm just going to leave them here for a second. If you're standing at point C, where theta is, what would you be looking at? What would be across from you? Who? What side is opposite of you? What side? It's a length segment. AB would be across from you, would be opposite of you, right? If I was standing at this point, or you were standing right there, you would be looking outward at this length right here, wouldn't you? That would be, it's kind of like, you know, me standing in this corner of the room, I look out and I see those two walls, right? I have a wall next to me, I got another wall next to me, and I'm looking at another wall on the other side of the room, okay? So, we call, wherever you're standing is the theta, all right? And the wall that you're looking at on the other side of the triangle, we call that the opposite side. Now, you have a wall to your left, you got a wall to your right. One of those walls is the hypotenuse. It's already got a name. We call it the hypotenuse. The other fellow, right? If you're standing at C, on your right is the hypotenuse, isn't it? And to your left is the other leg, right? Is the CB side, right? Are you imagining this? You with me? You picturing what we're seeing? All right. So if this guy is the opposite, this guy is the adjacent, the next door neighbor. So you have an opposite side, you have an adjacent side, and you have a hypotenuse. And all triangles, no matter where you're standing, whether you're standing at A or whether you're standing at C, has got a side that's on the opposite of you. You got a side that's adjacent to you. And the hypotenuse is always the hypotenuse. So it's just really a question is, who is the opposite and who is the adjacent? Now, let's imagine you're standing at this angle. That's where you're right now. Who's opposite now? CB on the other side, BC, CB, same thing. This guy is now opposite. And who's adjacent? AB. So it depends upon where you're standing. Okay? If you think about it, you have, I mean, whether you live in an apartment or whether you live in a single house or a townhouse or something like that, if you walk out your front door, the person across the street from you or across the hallway from you, that is opposite. And your next door neighbor is your adjacent. But if you were to walk on the other side of the street, now all of a sudden things have changed, right? Now people have different names, right? But they're still the same people, okay? So where your angle is determines who is what, and now this is why this matters, because we're going to talk about how that angle and how these sides are related. Get that out of your ear. And remember, this is the hypotenuse. Okay. Now, before we go anywhere, actually, no. We can do that next class. We'll do this first. Okay. Look on your calculator, and above the parentheses and the comma, you have three weird buttons that you've always looked at and wondered what they were. SIN, COS, and TAN. Those are abbreviations. And if I hear people use the words sin, cos, and tan, I'm going to yell at you. Because that's not what they're called. This is pronounced the sine of theta. Okay, you would pronounce it like you pronounce a stop sign, the sine of theta. It's not the sin, okay? It is sine. This is sine of theta. The sine and the cosine. And then the last one is the tangent of theta. Okay. Now, just so that we all know what we're dealing with, go to your calculator and type in the sine of whatever age you are. So the sine of 15, or the sine of 16, or whatever it is. Look at what you're going to get. What does it look like? Yeah, it's some ugly, evil, nasty decimal with no whole number on it, right? Okay? And that's what you're going to be expecting in a lot of places. So don't be freaking out when you see it, okay? That's what these numbers look like. And what are those numbers? Let me tell you. Watch. The sine of theta is equal to the opposite over the hypotenuse. So what I'm saying is, it's that if I know these lengths, okay, if that's my theta, my opposite, the length of my opposite side, whatever the opposite length is, divided by the length of the hypotenuse, it's going to be equal to that funky decimal. Okay? And it'll make a heck of a lot of sense when we actually do some. So just follow with me and copy this down. The cosine of theta is the adjacent and the tangent of theta is my opposite over my adjacent. These three ratios, remember, a ratio is nothing more than a fraction. Okay? These three ratios, these three things, are related to the angle that's involved. Okay? They're all related to each other, and this is what trigonometry is. Trigonometry is saying, okay, if I know a little bit about my triangle, I can find out a lot of other things about my triangle. Because you can imagine, if I changed any of those sides, if I made any of those three sides a different length, then angles are going to change too. So angles and lengths are related to each other. Okay? One other thing. This theta that you are looking at right there, it's a degree. Okay, it's some number of degrees, because theta is a measurement of an angle. So you can't take the cosine of 3 feet. It doesn't make sense. Sine, cosine, and tangent, they take in angles. Okay, and they spit out ratios. You can't plug in the cosine of 5 miles. I don't know what that means. But I can take the cosine of 5 degrees. Okay. Now, let's do one, just to show you what I'm talking about. Okay. Here's the process. This is a typical example of a problem that you're going to be using and solving today. Okay. This is what they look like. First thing you're going to do is you're going to figure out which angle do I care. Well, first of all, I need a right angle. Which angle is my theta? What is theta? 55 degrees. Okay. Theta is an angle, and it's the angle I care about. Okay. Who is the hypotenuse? The 10 is my hypotenuse. This process that I'm doing right now, where I'm saying, hey, this is my hypotenuse, this is my adjacent, this is my opposite, this is a big deal. This is how you do these. What is x? Is x opposite, adjacent, or what? What is it? Is it across the street, or is it next door? It's opposite. It's across the street, isn't it? My adjacent is right over here, and I don't care about it. It is not part of this problem. So doesn't matter to me. Okay. So look at my 3 ratios. Now, there's a shortcut way to remember those 3 ratios. Sohcahtoa. That's how you would pronounce that. All right, and I wrote it that way so that you will remember that sine, if you look at that one, the first one, the first group right there, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. This little shortcut, this little abbreviation, you should write on the boards. You should write it on your quizzes. You should write it on your formula sheet when you get it on the SOL, because it's not on the SOL formula sheet. You got to remember it. Okay, but you will do this so many times that you'll just know it. But still, this is one to remember. Sohcahtoa. Everybody say it with me. Sohcahtoa. Sohcahtoa. Come on now, y'all. Come on. We all need to wake up. Sohcahtoa. Say it like you just climbed out of the jungle, and the first words that you hear are Sohcahtoa. Say it with me one more time. Oh, y'all. Sohcahtoa. Yeah, say it from the gut. Right, there we go. That's awesome. All right, Sohcahtoa. All right. Now, okay. Which one of these 3 do I need because I got a hypotenuse and an opposite? Which one should I be talking about here? Sohcahtoa. So it's the sine, right? The sine. Don't you... Sine of theta is opposite over hypotenuse, right? Okay. Now, let's plug in the stuff that we know and solve for the stuff that we don't. And the opposite is x, and the hypotenuse is 10. So, I got to get x alone. So what am I going to do to get x alone? Multiply it by 10 on both sides, because I got x divided by 10. I want to get rid of the 10. So if 10 is dividing, I'm going to multiply to get rid of it. So go to your calculator, and you can type it in one line of commands. 10 times sine 55. Enter. 55, just like that. And you can close the back parentheses if you want to, but you don't really need to. 10 times the sine of 55. What did you get? 8.93. Okay. 19. I'm sorry. Yeah. All right. Now let's look at that and say, wait a minute, does that make sense? First of all, look at your picture. If the hypotenuse is 10, does that make sense that that length, that x, would be 8 or 8 and a little bit? Does that look right? You know? Right. So you can eyeball it just because you know that, I mean, if you had come out there with, hold on, I can do this. If your answer had been like 5.3, something like that, would it have worked? Would that have looked right? Like, could x be about half of 10? Does that look right? No, it doesn't, right? It's not half. No, too much. So if you come up with some weird number, you should always look at it in relation to the rest of the problem and say, okay, well, if this guy's 10, well, that makes sense, all right? Okay? How about this one? Okay, so first thing you ought to do is decide who is opposite, who is adjacent, who is hypotenuse. Write them down. And then decide if you're going to use sine, cosine, or tangent. Who is the 13? Yeah, it's the hypotenuse. I know that because it's across from the 90. And the x, is he opposite or is he adjacent? He's adjacent. He's next door, right? And obviously theta is my 40, right? Okay, so looking at Sohcahtoa, who should I be using? Which is the cosine. You would have remembered what would happen next. All right. Cosine is what over what? Adjacent over hypotenuse. All right, cool. Now, you know what theta is, you know the hypotenuse, you can plug in adjacent as x, and we can set up an equation and roll with this. So write down what you think the next step is. And if you feel strong about it, write down the next step. All right, so cosine of what? 40 equals what over what? Okay, cool. That's correct. Now, what about getting x alone? Multiply both sides by 13. X is approximately what? 9.95? Is that what I'm hearing? So, looking at the size of the hypotenuse, does it make sense that 9.95 is a good, reasonable kind of answer there? Right? Okay. Awesome. You just type it in just like this. You type it in just like you see. 13 times cosine 40, parentheses, enter. Huh? You just type it in just like you see it. 13 times cosine of 40. Okay. All right. So that's not so bad, right? Okay, what if I wanted the size of y? That's my opposite. So who could I use to get my opposite? Tangent. Not tan, tangent. You could use whichever. Well, actually, you know what x is now, right? You could use it if you wanted to. But what if you didn't have it? If you just wanted the opposite by itself, and you didn't have x first.
We already know what x is.
Yeah, you know what x is. You could use it if you want. That's fine. You could do either one. Which one do you want? I don't care. We haven't done a tangent yet, have we? Okay, let's do a tangent. Okay. Now, plug in what we know, solve for what we don't. If you're going to do this, you better give yourself at least a couple of decimal points. Right. Right. And now, so it should be something like 8, right? 8.3, 8.4, 8.34. And if you look at that, it kind of makes sense because it's across from the small angle. It's the smallest side. It could be. It looks like it's. I mean, my picture isn't exactly perfect. A 40-degree angle actually looks more like that. So now it really kind of does look like 8 if it needed to be, right? And let's just for fun, for the heck of it, because we know all 3 sides now, right? Let's do the Pythagorean Theorem. Just for fun, just to see if it works. And that should be equal to 99.25 And 8.4 squared, what's that? Yeah, but what's 8.34 squared? Who? 16, what? 0.55. And if I add those two numbers up, I should get approximately, what is it, 8, 0, 67, 167? Huh? 99 point what? 0025? Okay, and add all that up, and what do you get? You should be getting 167.5525. Now notice that there's some rounding error in there, right? Because 13 squared is 169, and 167 is close. You're off by a little bit, and that's rounding error. So the Pythagorean theorem would still roughly hold, okay? And if you gave yourself more decimal places and did this with more decimal places, you would have a better answer. Yeah. Plus. Huh? Oh. Yeah, I'm off a little bit. You're right. Good call. It was 168. Even better. So it's an even better approximation than we thought, right? So it's pretty close. All right. So all of this stuff is related. You got the Pythagorean theorem, you got trigonometry, you got all sorts of stuff. Now let's try something a little bit different. Let's see how well y'all are, how strong your algebra is. Who's my opposite? Who's my adjacent? Who's my hypotenuse? Write them down. Set up your equation. Pick what you're going to use. Sohcahtoa. Who am I going to pick? 9 is my opposite or adjacent or hypotenuse? It's opposite. X is my hypotenuse. So the sine of 65 is equal to my opposite over my hypotenuse. Okay, how do I get X out of there? By what? Times both sides by what? By what? By X. Now how do I get X alone? How do I get X alone? Remember, the sine of 65 is just a funky decimal. Because remember, the sine of 65 is some goofy decimal, right? It's like 0.9 or something. No, 0.8 or something, 0.8 something. And now you can go to the calculator and type 9 divided by the sine of 65, and you should get something in there. It'd be like 11 or something. 9.9? 9.93. And now, does that make sense? Could that be my hypotenuse? It's bigger than the 9, and it needed to be, because remember, the opposite, the hypotenuse is the biggest side, isn't it? I see kids year after year after year coming from all over the place who have a heck trouble right here, not knowing how to get the x out of there. I don't know why algebra doesn't go into this enough, but watch. Do we all agree this? 10 divided by 5 equals 2. Do we all agree? Okay. Do we all agree this? Isn't that true? Right? What? Okay. Thank you. So now look and see what happened between these two. All I did was just switch them out. Okay? Because the step that you're not seeing is this. I multiplied both sides by 5. And then divided both sides by 2 to give you that. Okay? So when you're dealing with fractions and proportions and stuff like that, you can switch diagonally across the equal sign. Okay? So when you have something that looks like this, and you've got to get the x out of there, look at what happened here, going from here to there. Pop. They just switch places. Okay? So don't freak out if you have an x in the denominator. Just switch it with the other side. Okay? Makes life simple. Try this one. And then you're going to the boards. So 20 is who? It is across the street. It is opposite. And x is adjacent. Who should I be playing with? Tangent of 57 is my what over my what? Opposite over adjacent, so who over who? 20 over x. How am I going to get x alone? Yeah, you can multiply by both sides, but let's take that shortcut. Just switch them out. And if you crunch that number, it should be like 8.7. Well, hold on. Okay, I believe you.
Do we round?
Yeah, just give it like 2 decimal places, and that's usually all right. You know, unless the instructions say round to the hundredth or round to the tenth or whatever it is, 2 is usually enough for me. But if you go into higher math or sciences and stuff like that, you know, physics uses this all the time. Okay, engineering, physics, any place where you're dealing with like a real life object and you're talking about like the sizes and shapes of real life things, you're going to be dealing with sine, cosine, and tangent. And since those measurements might make the difference between something on the assembly line fitting or not fitting, or, you know, will my reach far enough and grab what it needs to grab or something like that, you want to give yourself more decimal places, because like we saw with the Pythagorean theorem question earlier, a little bit of error, just rounding a little bit, created other errors. And you can imagine that a little error in the beginning of a big crunch of a calculation, you know, your satellite might not fly. You know, so the more decimal places, the better, based upon where you are and what problem you're trying to solve. It was 12.7, 98. Thanks. All right. So how do we feel about all this? Not so bad? All right, cool. This episode of the Ronco Show has been brought to you by Sine, Cosine, and Tangent.